Interpreting p-values. P-value is the tail area measured from where the sample statistic lies. The framework we're going to use here is a probability distribution. First, let's start off with a distribution. This line over here, this represents all possible values for the variable that we are analyzing. And right in the middle here is our hypothesized value. And let's just assume that this variable is normally distributed, which gives us this bell shape. Now, what p-value measures is the tail area from where the sample statistic lies. So first, let's look at the first sample. So let's just assume that the value for the first sample falls over here. So what p-value measures is, well, what's the tail area measured from that point? So corresponding with sample 1 is p-value 1 over here. But now look what happens as the sample deviates further from the hypothesized value. So the further that the sample lies from the hypothesized value, the lower the resulting tail area would be. And you could see that with sample 2, it's got a much smaller p-value because the resulting tail area would be smaller. Okay? And there it is. This sums it up. The further that the sample or test statistic deviates from the null, the lower the resulting p-value will be. But at the same time, that means that the t-statistic will be higher. If you recall the definition of t-statistic measures how far the sample deviates from the hypothesized value measured in units of standard error. So naturally, the further that the sample deviates from the hypothesized value, the higher the test statistic will be. And finally, the more that the sample statistic deviates from the null, the more likely it is that the null will be rejected. And here's the logic. We have two samples here. Sample 1 fell over here. Now, you can argue that, because these are samples, once you factor in the error, you can say, you know what, it's possible that sample 1 is close to or equal to the null after factoring out the sample error. However, for sample 2, it becomes harder to make the argument for sampling error because sample 2 is just way too far away from the null to attribute that distance to just error. Maybe sample 2 is very far away from the null because your hypothesized value for the null is false. And that's exactly what we're saying here. So the further the sample deviates from the null, the more likely it is that the null statement will be rejected. So now what we're going to do is we're going to put all these together and come up with a formal framework with respect to when we can accept or reject the null. And here it is. If the p-value is less than the level of significance, that's when we reject the null. And here's the logic. So here's an illustration to prove that logic. Suppose that the level of significance is right here. Okay. So, and what the level of significance does is it creates the goalpost for the null range. Okay. And this really is like a penalty kick. So if the sample falls anywhere in here, then we can attribute that to sampling error, and we can say, you know what, it's possible that the null is true. On the other hand, if the sample falls outside of the goalpost, then we'll say, you know what, that's no longer due to sampling error. The sample simply just does not support the null. That means the null is false and should be rejected. And that's exactly what we're saying here. So I have two possible p-values. For sample 1, you could see that the resulting p-value, remember p-value is the tail area, is greater than the level of significance, which means that the sample actually fell within the null range, and therefore we accept the null. On the other hand, if you look at sample 2, the resulting tail area, which is what the p-value is, was less than the level of significance, but you have to understand what that signifies. The smaller p-value means that the sample fell outside of the goalpost, and therefore we would reject the null statement. Okay? Now, tip, in a significance test, and what significance test means is the coefficient equal to 0 or not? And that's why we set the null as the coefficient is equal to 0. So the only question is, does the sample support this? In other words, does it fall within the goalposts? or does the sample refute that? In other words, the sample falls outside the goalpost, and there it is. If the p-value is greater than the level of significance, as was the case with sample 1, then we accept the null, which means that, and here's a null, so there's really nothing to memorize. So if we set this up properly, there's nothing to memorize. You just said accept the null. Then you look at the null. What does the null say? That the coefficient is equal to 0, which means it's insignificant. On the other hand, if the p-value is less than the level of significance, which is what we had with sample 2 right here, right? And then you could see that the sample falls outside of the null range, and therefore we reject the null. And if you reject the null, you have to go with the alternative. So if the null says that the coefficient is 0, then the alternative is that it's not equal to 0, meaning that it is significant.